Today's topic is on probability, how you will perceive the probability in daily life. It exists here and there, everywhere. Now, let me ask you how we will define the probability. Probability is the chance of occurrence of an uncertain event. And what is an uncertain event or what is an event? Event is the possible occurrence or any outcome. We sometimes have rare events. You may read different very interesting books like Fooled by Randomness and The Black Swans, where the writers have given the rare events and how they discuss them, like 9/11 as a rare event. But in our daily lives, things start happening here and there, and they are events. Probabilities. We have basically three types of probabilities. Let me ask, what is probability? Probability is the chance of occurrence of an uncertain event, and that lies between 0 and 1. Each possible type of that occurrence is an event. Like if you flip a coin, it either becomes heads or a tail. That event of flipping a coin gives you an outcome, either heads or tails. If you're trying to explain that event with a head, then, or you are just explaining it with the tail, it's a simple event. Now, the probabilities can be assessed in three different ways. The first one, we have a priori classical probabilities. The second one, empirical classical probability, and the last one is the subjective probability. In the first one, where we call it a priori classical probability, we have a kind of probabilities where outcomes are known, or the total number of outcomes are known. Like deck of cards, we have 52 cards with us, and we know the number of reds and the black ones. Now, we can say something about this process and these probabilities in advance because we know the outcomes. Then the second one is empirical classical probability. Now, in this case of probability, this type of probability, we have an observed data, like you are going to see that you are launching a new product, how many people are willing to buy this or planning to purchase this product, how many voters are interested to give vote to any party, or there are so many other examples. And then the last one, we have subjective probability. In subjective probability, we'll generally come across a situation where we don't have any kind of probabilities in existence, or the case is totally a newer one. Like you are brand manager or CEO of your organization, and the team leader, who is the research and development head, assign a probability of success to that product, maybe 60%, but you as a CEO assign it a different probability, that may be 30%. So that all goes to the subjective opinion of person, and that varies. And we generally go for subjective probability because we don't have a priori classical and empirical classical probability. Now, let us start with what is a sample space. A sample space is the collection of all possible events, like all 6 dice, faces of a dice, all 52 cards of a deck, So they are our sample space. A simple event is an outcome from a sample space with one characteristics. As in our example, heads with a flip of coin. And the complement of an event is all outcomes that are not part of any set or A. And joint event involves two or more characteristics simultaneously. We have different operations. The first one I would like to say is union, intersection, and complement. We have a set A with the elements 0, 1, 3, 5, and then we have set B with elements 2, 4, 5, and 6. And I just want to do these operations on these two sets. For the sake of complement, let me say we have a universal set. That is a universal set, and it includes 0, 1, 2, 3, 4, 5, 6, and 7. The first one, when we have a union operation, A union B stands for, where we have A and then union B, it will give us, like, let me put it like this way. Now, with these both operations, we have, with these both sets, with this operation 0, 1, 2, 3, 4, 5, and 6. Now, the important thing that comes with us is this 5. We have just used it one time at this place. So it shows that there is a union. Or if I just draw like this way, a diagram, our 5 lies somewhere here, and the rest 0, 1, 3, 5, and then 2, 4, 6. So this union is the whole area. So this is the first one. We have union operations. The second one, I'm moving towards the second one, where we have intersections. And how we will proceed for this? Again, the set A, that is 0, 1, 3, 5, and the set B, that is 2, 4, 5, 6. So A intersection B stands for, we have only intersection is 5. And on the Venn diagram, let me say like, these are the two areas where in the first one we have 0, 1, 3, and somewhere here 5, and in the second one we have 2, 4, 6. Now this is the area that is intersection. We have this complement stuff. In complement, we let me say A complement. I have to find out what is an A complement. In terms of A complement, I will use union. This is not a union. This is universal set, which I just said that this one is a universal set, and I am just subtracting the set A. So I have the set 0, 1, 3, 4, 5, and 6, and then I am subtracting A out of it. So after subtracting this, like I'm just removing these elements. I am left with 4 and 6. So this was our complement. With this introduction of union, intersection, and complement, we can now move onward to our contingency table, and I'll show you that how we will move further with these sets. How many people have bought these televisions? Because in your previous studies, you have seen that the people are interested or they are planning to purchase. And few of them after a year time have purchased. Few of them, those who planned, they didn't purchase. So this is a kind of mix thing, that how you will assign the probabilities. And in this case, if we have done a survey of 1,000 households, let us see how we can just assign these classifications. Though we will discuss the simple probability, simple marginal probability, joint probabilities in upcoming section. But if you can understand the contingency table, which is a cross classification table, then I hope you will have no problem while understanding any other concept. I've just written down here that this is a two-dimensional thing. The first one, we have those who actually planned to purchase a high definition television sets, and those who were planned to purchase a high definition television sets. Now we are just assigning the probabilities. Number of people, those who said that yes, they actually purchased your television, and in your previous studies they planned to purchase, they are 200. Those who actually purchased, this comes from this side, actually purchased, and they also plan to purchase, this is our 200. Those who actually didn't purchase, but they plan to purchase, is 50. The second thing, those who actually purchased, but they didn't plan to purchase, they are 100. And this is the number, those who didn't plan to purchase, and then afterwards they haven't purchased it, they are 750. Now this is the place where we have joint probabilities. Joint probabilities are, on this intersection we are defining any variable, anything with two characteristics, with actually purchased and planned to purchase. This is a joint probability stuff. And this is where we will just sum up that how many number of people have totally purchased this. It's a simple probability. Like we have 250 who plan to purchase. So we have 750 those who didn't plan to purchase. Similarly, those who actually purchased are 300, and those who actually didn't purchase, they are 700. Now when we say the probability is in between 0 and 1, in this case the total sample size for which we are looking for our probability is, the total sample space is 1000. Either you will sum up from this side, like, or either you just sum up from this side, it will be 1000. Now it's just to tell you that how these operations work. Joint probabilities. And those who lies at the corners, they are simple or marginal probabilities. So this is the basic concept that goes to our contingency tables, which shows that how we can assign these probabilities. Same is the case for this one. The total number of sample which we did was 1000. And now we are moving onward. Either we can take this side or either we can take this side. It doesn't matter. Now, here we have people who plan to purchase. We can say either in terms of yes or no. If they say yes, they lie here. If they say no, they lie here. So in terms of yes, this is yes, we have 250, and in terms of no, we have 750. So this is the point where we have 250, and this is the point we have 750. And we are moving onward. Now, the next thing is, at this branch, we have those who actually purchased. Here we have yes and then no, and again yes and no. Those who planned to purchase, they were 250, and actually purchased, where we say yes, they are 200, and those who said no, they are 50. Again, in this case, those who said no, in terms of plan to purchase, they said no, and we have, again, from them, those who said yes, they are 100, and those who said no, they are 650. Let me total this, and it comes again to 1000. And probability is the mutually exclusive and collectively exhaustive. We say that an event is a mutually exclusive when event that cannot occur together, like day and night. They cannot occur together. If you flip a coin, it can be either heads or tails. So you can't have both heads and tails at the same time. Collectively exhaustive. In collectively exhaustive events, we say that if both events cannot occur together, then the next thing is one has to occur. If you are flipping a coin, if it's the point is that the heads and tails both cannot occur at the same time, but one has to occur, like heads has to come or tail has to come. So we can't get away with this thing, that one event has to occur is collectively exhaustive. The probability is a numerical measure of likelihood of an event that will occur. Probability generally lies between 0 and 1. And in the cases when we have mutually exclusive and collectively exhaustive event, the sum of all probabilities lies between, and its accumulation comes to 1, and it can't go away with it. How we can compute the joint and marginal probabilities, as I have already shown on this contingency table, that we can have marginal and joint probabilities. Let me show you just on for a while on this graph that how these are the marginal and simple probabilities, that these points these are our joint probabilities. Let me say this. If I'll just say this is my B1 and this is my B2 and this is like A1 and this is A2. So marginal probability of those who plan to purchase is of A1 and B1 plus A1 and B2, and that all goes to this point, that will be 250. So with 250 we got 250. These are our joint probabilities. When you say and talk about marginal probabilities, these points here, like this 300, this 700, 200, and 750, all of them, they are marginal probabilities. General addition rule, when P probability of A or B is equal to probability of A plus probability of B minus probability A of A and B. And if we have mutually exclusive events, then this P of A and B is nullified and it goes to 0 because they lie at the intersection. So we can just simply get away with this thing. A very important next topic comes with how we can find out conditional probability. Let me introduce you first with how to the terms or how you can understand, and then we will go for a simple example, and I hope it will help. When we talk about conditional probability, from its names, it shows there is some conditions, something involved, some prerequisite involved before going into that discussion. P of A given B. Now, this point we will call it as given, and we can say it probability of A given B. And if you just, if we are trying to open it, probability of A and B and probability of B, because this is the precondition or the condition already with us. 60 years old, and then they have this thing which is heart disease. So now we can find out the probabilities with this simple example. We can also use contingency tables for this as well. Okay, we are interested in conditional probability, and here is a simple example. When probability of A given B, then P of A and B and P of B. And the last thing is 20% have both of them. So we are trying to calculate the probability of the cars having AC given that, and we have to calculate the probability of finding the CD players in these cars. So I'm looking for probability of CD players when AC is given in any car. Now I'll use contingency table again. Where we have a CD player on one side, and we say yes, car has CD player, or no, it doesn't have CD player, and we'll use the terms total here. And we have air conditioning. Some of them have AC and some of them don't have AC. And here we have the total with us. So this is the point where we have 0.2% or 20% probability that they have both CD and AC. And out of which 70% those who have air conditioner, and 40% those who have CD players. So if I say the total probability is always 1, so can we just find out these values here, like this one, and this one? it's a simple complement thing with which we can just simply calculate these values. Like for this point, if I subtract 7 and minus 0.2, it will give me 0.5. Similar is the case, I'm just taking complement and it will give me 0.2 here. It's just subtracting from 4. And then at this point, I can just say 1 minus 0.7, it will give me 0.3. And then 2 plus 1 gives you 3. And if we sum up this, we'll have 6. So now if you start totaling this thing, it will give you 1. Given AC, probability of CD and AC and probability of AC. So what is the probability of having AC? This is the probability of having AC. Probability of CD and AC, that is this point, which is 0.2. So our results comes out 0.28. Here is an example of how to use this conditional probability. And if you just see this screen, I've just calculated this thing on your current screen. This is where we find out conditional probability, and this is how we will while using a decision tree. We have both dimensions. On one side we have air conditioning, on the other side we have CD players, and I have already made contingency tables, and from this contingency table you can simply transform this thing to your decision tree. We can have both of them here. Sometimes we have statistical independence when event A and B are independent, when the probability of one event is not affected by other. And this is like, it's very simple. Like if you flip a coin, the first time it comes out heads. Now when you do this second time, will it be dependent on the first one? Not at all. It will be either heads or either tails, no matter what was the first outcome. Then we have a simple multiplication rules, where we are just simply using cross multiplications from the table. A very, very important thing for our today's discussion is Bayes' theorem. In terms of Bayes' theorem, we have already a kind of a priori classical probability when we assign a probability to different things. And then later on, we just try to change these probabilities or want to revise these probabilities that on the basis of empirical evidence, on the basis of certain studies, and then we realize that we should either change this, we should assign a different probability to that thing, and it will affect differently to our decision making. I'm here introducing a simple case study that is with the drilling company, who has estimated a 40% chance of striking oil for their new well. This is a kind of a priori probability assigned. Probability of S of D and the probability of detailed test when success is given, probability of successful test, probability of detailed test given successful test, probability of successful test plus probability of detailed test given unsuccessful test, and probability of unsuccessful test. So in simple terms, this is how you write down your Bayes' theorem. Now let me plug in the values which we have just calculated. We have this value with us, that is 0.6. We have this value with us, that is 0.2. Again, we have all these values already with us. And what we have to do is just simply plug in. For this value, we have 0.6. For P of S, we have 0.4. For detailed test, when S is given, this is 0.6. Similar is the case, we have 0.4 and 0.2 and again 0.6. Now these values are coming from this point and this point as well. When you multiply them, you will get the results like 0.24 and it will be 0.24 plus 12 and the results will be 0.667. What was our initial probabilities, or before this detailed test, what was our probabilities given in our successful well striking case? In that case, you will see it was 0.4. So after this detailed test, we find that it's now 0.6 or 66% probability. That has increased from 40%. So we have just revised the probabilities while using Bayes' theorem. Marginal probabilities, joint probabilities, conditional probabilities. There are few interesting things when we talk about events. You must consider there are pros and cons, and sometimes we have a rare event. 9/11 was a rare event. The invention and the utility of the computers was initially thought as it was not of any use, but it has revolutionized our thought process. So I would like to recommend, if you can just go and read very interesting books like The Fooled by Randomness and then The Black Swans. You will really enjoy them because they are relevant with today's discussion. Thank you very much. If you have any questions and comments, please do write an email to me. Thank you very much.